So let's take the diffusion rate Dij. This time, this particular term requires modeling because this has a lot of unknowns, and we have three terms here: the pressure diffusion rate, viscous diffusion rate, and turbulent diffusion rate. So pressure diffusion rate, we have similar argument like in the when we model the pressure diffusion rate of turbulence kinetic energy. What did we do there? Sorry, the pressure diffusion rate of the turbulence kinetic energy, was this modeled? No, we did not model. So what is the argument that we gave? Yeah, so we said this is very small compared to the other terms in simple canonical turbulent flows, and it's also not possible to measure this in experiments. So giving this argument, it was ignored. We did not model this, but I did show you the data where if you deviate away from a smooth surface, where let's say you introduce some roughness or some obstacles, flow separation, the pressure drag is very important there. So the pressure diffusion also becomes very large. So, but we were going to use the similar assumption here. The pressure diffusion rate is also omitted in this equation here. So the pressure diffusion rate, the first one is pressure diffusion rate. Okay, so this particular term is minus dou by dou xk of, you have p prime uj prime by rho delta ik plus p prime ui prime by rho delta jk. This term is neglected again for the same arguments. This term is neglected again with the same arguments. That is difficult to measure this, right? So not possible to measure in experiments because it's a correlation of pressure fluctuation and the velocity fluctuation. So that is not possible. And the other argument is that in from the DNS data, we see that DNS data shows that it is small compared to the other diffusion rates in simple, or I can just say canonical shear flows. So therefore this is neglected, not modeled at all. Okay, not modeled. We are omitting the pressure diffusion rate term. So we have turbulent diffusion rate and the viscous diffusion rate. So the second one is, let's say, the viscous diffusion rate, which is dou by dou xk of nu dou ui prime uj prime average by dou xk. Do we need to model this viscous diffusion rate? No, because Reynold stresses are available here, just like the production rate term, right? Modeling is not required here. The term is readily calculated. Okay, so no need to model since ui prime uj prime is available to us. The Reynold stresses are available to us, so we can just like the same argument as the viscous diffusion rate of turbulence kinetic energy, that was dou k by dou x j there. Okay, j was the repeated index. So so far it is straightforward. Then that means we have another term which is the turbulent diffusion rate, the 27 turbulent diffusion rate. This cannot be ignored because in a turbulent flow, the turbulent diffusion dominates. Turbulence also transports. In addition to it dissipates, I told you, right, it also transports. So turbulent diffusion rate is very important. And if you recall how we modeled a turbulent diffusion rate term for the K equation, we use what is called a gradient diffusion hypothesis, analogous to your Fourier's law of conduction, right? So we are going to use that, but we will see that there is slightly a different option here. We can fall back to the original option, or we can slightly make it little better. Okay, so recall the gradient diffusion hypothesis. Used while modeling K equation, right? So in the K model, what did we do? The K model equation for modeling the turbulent diffusion rate term, which was minus half ui prime uj prime average, right, dou by dou x j of this term in the K equation. I am talking about going back to the K equation now first. So dou by dou x j of this particular term was modeled as nu t by sigma k dou k by dou x j dou by dou x j of that. So this particular correlation term was replaced by a gradient diffusion hypothesis, that is where we use this nu t by sigma k was an isotropic diffusion coefficient. Okay, so where nu t by sigma k was isotropic diffusion coefficient. So it's dimensionally consistent. We continued in the K equation model like this, but there was an issue here, especially when we come to Reynold stress modeling. So we will see that this equation now essentially assumes that if diffusion along the xj direction is 0, for example, then the total diffusion can go into 0. So I mean, it essentially looks into the gradient dou k by dou xj. So if dou k by dou x1, let's say, is 0, it assumes that there is no diffusion. We are essentially that is the whole modeling point of it, that we are looking into a gradient of that one. Gradient becomes 0, diffusion becomes 0. To save that, we have another option here. So here let's say call this equation 1. Note that equation 1 assumes that if gradient along xj direction is 0, then the diffusion rate is 0. So to save this, we would like to introduce an anisotropic diffusion coefficient. Okay, so we would like to have what is called an anisotropic diffusion coefficient here, or we can consider a general gradient diffusion hypothesis. This is given by, this is the reference, Daly and Harlow, 1970. So according to this general gradient diffusion hypothesis, we will make use of an anisotropic diffusion coefficient instead of this eddy viscosity, nu t. So what we do is we model this dou by dou xj of minus half ui prime uj prime. This is modeled as we essentially take dou by dou xj of, I take another term here, anisotropic diffusion coefficient, which is Ck, a model constant, k by epsilon, a time scale introduced to make dimensionally consistent form, and the anisotropic diffusion coefficient, instead of eddy viscosity we use Reynold stresses, because Reynold stresses is being calculated, which represents the anisotropy in the flow. So the Reynold stresses comes in here, which is uj prime uk prime average. Okay, and then your dou k by dou xj. So here you had nu t by sigma k, that is the isotropic diffusion coefficient. That is being now replaced with uj prime uk prime, which represents the, so this represents the, or contributes to, accounts for anisotropic behavior. Nature of turbulence, and k by epsilon is introduced for dimensional consistency, a time scale, introduced for dimensional consistency. Okay, so this particular term is what we have here. This is your anisotropic diffusion coefficient. So the dimensions has to be the same on both the sides here. If you look into it, it has to be consistent. So whatever has appeared here, instead of mu t by sigma k, if you go and look into it, you would get the same dimensions as the mu t by sigma k. So this is the idea of this, introducing an anisotropic diffusion coefficient in the k model equation. One can do this. Now we will use the same idea to model the turbulent diffusion rate of the Reynold stresses. Okay, so similarly we can say, now before that we have to justify, right? We just said that the diffusion goes to 0 if gradient along xj is 0, right? If gradient along xj direction is 0, diffusion is going to 0. Now you see how does this save here. So we can say here, for example, in the j direction, wait, there is a change here. There is some, okay, this has to be, this is, there's a tensor rules are being, tensor rules are not correct because j is repeated thrice. Okay, so this is dou by dou xj, this is okay, this has to be different, dou xk here. Okay, j was repeated thrice, yes. So this particular part is included, so that this is a sum of now 3 terms. So dou by dou xj, if I expand it now, you will see. For example, if I take this as the direction x1, right? So here if I take x1 direction, I would get it as ck k by epsilon. If the k is the repeated index, we will say that this is uj prime u1 prime dou k by dou x1 plus I have ck k by epsilon uj prime u2 prime dou k by dou x2 plus ck k by epsilon uj prime u3 prime dou k by dou x3, right. So now even if dou k by dou x1 is 0 in one of the directions, the other two directions will save this one here. So it's a sum of 3 different terms there. Okay, so the gradients are even if it is 0 in one direction, the other two directions can save you, right. So that's the advantage here. The term that is inside, I'm not looking into the dou by dou xj of this. The internal term itself has sum of the 3 terms here. Here the whatever is in the round bracket, that was only dou k by dou nu t by sigma k dou k by dou xj. So in that particular gradient is 0, the entire thing will be 0, that particular term. Now that term is now sum of 3 terms. So even if gradient is 0 in one, it will be saved here. Okay, so the anisotropic diffusion will help, correct? Okay, so now I'm going to use the same concept here to model the RSM. So similarly, I can say modeling the turbulent diffusion rate in the RSM equation. So we can say that the dij term here, not the dk, okay, dij, let us say T, or the turbulent component, dij turbulent component, this is essentially dou by dou xk of minus ui prime uj prime uk prime, the 27 unknowns. This is now being modeled as analogous to what we did here, the general gradient diffusion hypothesis. I will have dou by dou xk, okay, and then I would take ck, the model constant, k by epsilon at time scale, and then I will introduce the Reynold stresses, which is uk prime um prime here, followed by the Reynold stresses ui prime uj prime average by dou xm. There k was introduced in the k equation, right, repeated index k, so that there is no tensor rules not being followed. Here m follows here, so it's a sum of 3 extra terms basically. K is the divergence term, but m is introduced, so that this is sum of 3 terms here internally inside, right. So k is also repeated, but for let us say dou by dou x1, when k equal to 1, this is sum of 3 terms, plus when k equal to 2, it is sum of 3 terms, so it will be like sum of 9 terms. So again the same argument here, this is introduced for anisotropic diffusion coefficient, right. So this particular part here is the anisotropic diffusion coefficient. Okay, but we have to check that whether it's dimensionally it is correct or not. So here I get meter cube by second cube, meter square by second cube. That's what I get here. Do I get this here? Is important. It's this last part is Reynold stresses, meter square by second square by meter. So that I get meter per second square. This is meter square per second square. K by epsilon is second meter here. So I get meter square per second cube. So dimensionally consistent, and this particular K by epsilon is actually introduced for that to make it dimensionally consistent. But there is a problem. This particular if you implement like this, now the question comes, why did we do this? This is great, anisotropic diffusion, but we did not do this in the K modeling equation. That's because this introduces numerical stability issues. So when you implement like this, it leads to, it's already strongly coupled, this leads to some coupling issues, but one can try it out. For a given problem it may work. Okay, so one issue here is that this is numerically unstable. May not be in all flows, but one can try it out to see. In general, it is numerically unstable to use this form of modeling using an anisotropic diffusion coefficient. So what we do is, this is of course option 1 to model. The option 2 is to fall back to the isotropic diffusion coefficient like before. Okay, so the option 2 is to go back to option 2 is to again use isotropic diffusion coefficient. That means the model is the dou by dou xk of your minus ui prime, uj prime, uk prime. This is now modeled as dou by dou xk of the mu t by sigma k, dou ui prime, uj prime by dou xk. Numerically stable, but we have introduced isotropic diffusion coefficient, or I can easily say it's here, it's already here, nu t. But where do I get nu t here? This we are solving for Reynold stress model. We can use the same formulation, right? K square by epsilon, but I don't have to model K here. What is K? Sum of 3 normal stresses divided by 2, that is available to you. So you are computing the turbulence kinetic energy. So mu t is lot better here, you don't have to model it, but the formulation you can use for mu t, right? So nu t you can still use it as, say nu t is K square by epsilon term. You can introduce C mu if you like or not, that depends on the model, but K and epsilon are available to you. Or I have not talked about epsilon, but at least where K is sum of your stresses. So this is available to you, being computed, so it's available. So this is numerically stable, okay, numerically a stable option while computing, but other can also be used, anisotropic diffusion coefficient. Many flows it may work.